So now I want to show you how to divide using synthetic division. Synthetic division is a shortcut. So it is a shortcut for long division, but it doesn't work in every case. It only works if you're dividing by something of the form x minus c, or x plus c is okay, your c would be negative there. But it doesn't work if you have a square there or a cube, or if you have a number in front of the x. It has to be a very specific kind of divisor. So in this case, we're going to set up our division a little bit different. I have the basics directions here for the setup, but I think it'll be easier to go through an example as we read through them. So for example 5 here, we're going to use synthetic division to divide this polynomial by x minus 3. So notice that we're in the correct form, x minus c. So our c here happens to be 3. Again, synthetic division only works for divisors of this style. It doesn't work for anything more complicated, and you would have to do long division in those examples. So what we do is we set it up like this. So your c value is 3 here. So you set the 3 up on the outside. And then we put also just our coefficients on the inside of the bar. Okay, so here our first coefficient is a 1. Then we have a positive 4, a negative 5, and then a 5. Now, if you were missing a term, you would want to fill in the 0 like we did in the last example, in the last video. We don't have any missing terms here, so we don't have to worry about that. Okay, so that's our first step. Write the division setup using the coefficients only, making sure the polynomial is in descending powers and 0 is used for any missing terms. So you have your c value on the outside, and then you have just your coefficients on the inside. So what you're going to do is the first step is you're actually just going to bring down the first number. Okay, so we're going to write the leading coefficient of the dividend on the bottom row. That's this right here. That's this. Just bring that first number down. Then what you're going to do is you're going to multiply the c by this value and then write the answer in the next column. So 3 times 1 is 3. Next, you're going to add those values together in this column here. So it's important to watch your signs. 4 plus 3 is 7. And now we repeat the process again. So I do 3 times 7, which is 21. I add my columns here. So I'm looking at 21 plus negative 5. So I'm going to have 16. And then 3 times 16 is 48. And 48 plus 5 is going to be 53. So we repeat this so all columns are filled in, which we have. Now we're actually done. So the degree in the first term right here of the quotient is 1 less than the degree of the first term in the dividend. So here we had x cubed, right? So this is a cube. So then this will be a square. So you start 1 less. So what we have is that x cubed plus 4x squared minus 5x plus 5 divided by x minus 3 is equal to, so this is my square, so it's going to be 1x squared plus 7x plus 16. And yeah, I'm just going right down the line with my variables. So if it's x squared first, x would be next, and then the number. Now, if you have something left over, then this last piece is your remainder. So if you've used all your variables, you have the constant at the end, and you still have an extra value here, that's your remainder. So it's going to be plus 53 over x minus 3. Okay. Here, that 1, you don't really need the 1 there. If you just wrote it as x squared, that would also be perfectly fine. All right, let's do another one. This is a good one too. If you feel pretty comfortable, you can always pause it after we do the setup, see if you can do the steps. So here, notice that I actually am in the correct form. So this does work. It's just that my c value is -2. So as long as it's just an x in the front, no number out front, like a 1x, plain and simple, then the other constant will be fine. If it's the wrong sign, you just use the negative. So instead of being 2, our C is going to be negative 2 here. So negative 2 is going to go on the outside. And then here, just be careful, you are missing the x squared term. So you want to make sure you put a 0 in for that to hold the place. So our largest degree is 3, so we start with the 5. So we have 5, and then the squared term would be 0. The x term is 6, and then the number is 8. Oops. And then I like to put just a little kind of line on the bottom just to stay organized. So we're going to start by bringing that 5 down. Oops, let's use blue. And then we're going to multiply. So negative 2 times 5 is negative 10. Add the columns. So 0 plus negative 10 is negative 10. Multiply. Negative 2 times negative 10 is positive 20. Add the columns. 26. Negative 2 times 26. Let's see, that's going to be negative 52. Just double checking my math. Add it with the 8 and we get negative 44. Now we started with a cube here. So that means our answer will start with a square. So it's always 1 less. If I started with a fourth, my answer would start with a cube. So just 1 less. So 5x cubed plus 6x plus 8 divided by x plus 2 is going to be 5. And this is going to be squared. So x squared minus 10, and then the x term comes next, plus 26. And then again, in this case, you have a remainder. So it's minus 44 over x plus 2. Now, if you don't like synthetic division, then you can still do long division. Long division will always work. So it's kind of a nice alternative if you don't want to use synthetic division. It does take a little bit of getting used to, right? Because it's a new process and maybe it doesn't make sense. It's more like an algorithm where we know how to do it the long way, we know how to do long division, and now we've created a shortcut way to just get to the answer, even though maybe the process doesn't quite make sense how it works, right? Whereas I think with long division, even though it's maybe a little bit more annoying to do it with polynomials, we know long division, like we understand that process. So this is nice. If you can learn the steps, it's going to be a lot faster for you. But if you don't want to use it, that's okay too. Just remember that synthetic division only works in very specific cases. It does not work for every case. So you can't always use it. All right, let's talk about a couple other little things here, like little definitions and stuff. So the division algorithm for polynomials, which we've actually already been using, it says let f and d be 2 polynomials, and the degree of d is greater than 0 and less than the degree of f. So basically we're saying we're dividing 2 polynomials. F is the numerator, d is the denominator. Okay. And what happens is when you divide them, you end up with this right here. And we've actually seen this already. So I showed this to you back in the last video when we talked about doing the check. You're left with a divisor, a quotient, and then you're adding a remainder. And that's what you see here. So when you go ahead and divide, D is your divisor, Q is your quotient, and then R is your remainder. And it's always of that form. So your function always breaks down into your divisor times your quotient plus your remainder. If you want to actually write it out to check your answer or something like that. Now your remainder could be 0. So it could be 0 here. Or of course, the degree of it should be less than the degree of your divisor, right? Because we can't divide any more. The remainder theorem goes a little bit step further with this idea. And it says that if a polynomial is divided by x minus c, so that very specific kind of divisor, like we just saw in synthetic division, then the remainder is actually equal to f of c. So in that case, again, you have a very similar setup, but your divisor here is this form, and then your remainder is the value of c when you plug it into the function. So let's actually just show how this works. So we have our function here, and we're going to use the remainder theorem to find f of 2. So let's go ahead and do that. So for the remainder theorem for f of 2, if you look at the setup here, then your C would tell you what your divisor is. So that means our divisor is x minus 2. So the 2 here is in reference to the actual divisor, right? If this was negative, then this would be a plus instead. So whatever number is here is always x minus that number. So this fits synthetic division. So let's go ahead and use synthetic division here and actually divide this out and see what we get. All right, so I'm going to use the 2 on the outside. And everything is in order. So I have a 1, I have a -4, a +5, and a +3. I don't have any missing terms, so I can kind of jump right in. I bring down the 1. 2 times 1 is 2. Add these together, I get -2. 2 times -2 is -4. Add these together, I get 1. And 2 times 1 is 2, which is 5. So if I write out my answer here, this was a cube, so I'm going to start with a square. Then I get that my original function divided by my x minus 2 divisor, my answer is going to be 1x squared minus 2x plus 1. And then my remainder here is this 5, right? This 5 over x minus 2. So in this case, my remainder is 5, right? Just kind of looking at that value. So what this tells us then is that f of 2 is equal to 5. Now, you're probably saying, well, we can already find that on our own, and I know that is true, right? So we do have the old way to find f of 2 by going into our original function and just plugging it in. Here I get 8, and then 2 squared is 4. So I have 8 minus 16 plus 10 plus 3. 8 minus 16 is -8. 8 plus 2 plus 10 is 2. Excuse me, I'm jumping ahead. And then I still get that same answer of 5. So you can see that they match. I know this is probably much easier in many cases than actually doing division out, but it's just kind of a nice correlation between the two ideas, that when we plug in an f value, this is actually equal to the remainder if we divided that original polynomial by that particular divisor. So we can do this for any number. What if I wanted to find f of 1, right? Then I could let my divisor be x minus 1. Or what if I wanted to find f of 10? I could let my divisor be x minus 10. So even though maybe this is a longer way to do it, it's really an interesting correlation here that we have, that sometimes evaluating also relates to division in a way, right? Or into factoring. So it's a nice relationship that we see between the two ideas. The last definition here I have is the factor theorem, which again kind of builds on this idea again. And it says that if f of c equals 0, then x minus c is an actual factor of f of x. And vice versa. If this is a factor of f of x, then f of c equals 0. Note that when f of c equals 0, this means that the remainder is 0. And again, I kind of mentioned this already in the initial video, right? I mentioned that, you know, if you have, I'm going back to our example 2 here, if you have no remainder, then that polynomial factors as the divisor and the quotient. And that's really what we're saying here, is that if the value at c is 0, then this is a perfect factor. So you actually can factor the polynomial using that as one of your factors here. So let's do an example with that. We're going to solve the equation 2x cubed minus x squared minus 11x plus 6 equals 0. And we're told that 3 is a 0 of the function. So if something is a 0 of the function, remember the 0 refers to the x value here. So this means that when we plug in x equals 3, we get 0 out. So this tells us that f of 3 is equal to 0. That's what this is telling us. So when you have something as a 0, it means that when you plug it in, your output is 0. So that number is your X value here when you go ahead and you plug it in. So that's kind of our first step, is to recognize that. So if f of 3 equals 0, then by the factor theorem, right here, x minus 3 is a factor of f of x. So what I can do, if it's a factor, I should be able to perfectly divide this out with no remainder. Again, notice that we're in the form for synthetic division. So if you're willing to learn the steps for synthetic division, it can definitely save you a lot of time in the long run. So here I have 2, -3, -11, and 6, making sure all your powers are in order. Again, notice that the function and the equation are the same, just that one side equals 0, and that there's no missing values. Bring down the 2. 3 times 2 is 6. Add these together, I get 3. 3 times 3 is 9. Add these together, I get -2. 3 times -2 is -6. And I get a 0, which is good. I should have a 0 at the end because my remainder here is supposed to be 0. This happens to be a cube, so I'm starting here with a square. So what I see here is that this becomes 2x squared plus 3x minus 2. And again, my remainder here is 0. So now how does this actually help us? Let's go back to the question. So the question wants us to actually solve this equation here. So we're trying to solve 2x cubed minus 3x squared minus 11x plus 6 equals 0. Now, so far with polynomials, we don't really know how to do too much. We only know how to solve polynomial equations by factoring. So that's why this is important, because I have found a factor, right? This is a factor. So this factors into x minus 3 as one of my factors, and then this as my other factor. Now, hopefully, because this is a square term, you should be able to factor this, the rest of this on your own without using synthetic division again. So at this point, if you just have a square, you want to kind of think about, okay, well, what could be my possible factors here if I want to keep going? And the ones that are going to work are going to be 2x minus 1 and x plus 2. So you would want to see if you could keep factoring and factor as far down as you can. If for some reason you can't factor, you could still set each factor equal to 0 and then use the quadratic formula to solve instead. Here I am completely factored, so I can solve the equation by setting each piece equal to 0. So x equals 3 is one answer. X equals 1/2 is another answer. And x equals -2 would be the third answer here. So we were able to use the fact that we knew we had a 0, use that particular value to factor out at least one of the factors here, right? That x minus 3. So then that way I have something that I can work with now. Whereas something that's a harder polynomial is a lot more difficult to try to just factor. You could try grouping method there, but if that doesn't work, then you're kind of stuck with trial and error. So this is a nice technique. If you have a 0, then we know we have a factor and we can go ahead and take that out. The other thing to note, remember we've learned before that the highest power actually tells you up to how many real solutions you can have. So because I have a cube here, it makes sense that I could have 3 real solutions. Now, just to kind of keep throwing in review for you, you can also graph this. So if you graph this function, because I have 3 real solutions here, or 3 real zeros, you would see those as x-intercepts as well on your graph. So we're really building the information at this point and kind of putting it all together. So we know zeros or real zeros and x-intercepts are the same. So I can see a lot of these things on the graph. And now we know that zeros are also related to factors. So if I know where my zeros are or my x-intercepts are, I can actually use those to help me start the factoring process so that I'm not just trying to guess out of nowhere or maybe not out of nowhere, but just kind of guess at what my factors are, I have a place that I can start. So this all really relates together, and we can bounce back and forth between graphs or equations or factors or intercepts, and help us to learn more about that polynomial.